Now, the way I created this is based on the homework and the quizzes. Nothing here was meant to be troublesome, but I think because I guess people are doing, from what I was talking to somebody yesterday who was a student, people aren't doing much until before the quiz on Friday, and then, I mean, some are. Some obviously are doing very well in this class. I had I had, I don't know, maybe 20, 25% very high grades. I'm not really sure of that, so don't quote me. But then I had a whole bunch of people that there were great gaps in their understanding. So I want to go through this test with you and make sure we're clear on this. Because this was not meant to be a difficult test. And I'm not sure where the real problem lies. So the first problem is based on homework I gave you. I think the values were changed slightly, but that was it. I'm going to put... Y'all don't see an eraser around here, do you? Anyone? Anything in the back or anything? Normally you have an eraser in the rooms. Okay, so for the first one, it's a non-magnetic material may give age. Let me make sure you understand this. You're going to see this again, and I want to be clear about that. You're going to see this again. I'm going to show you a few other things you're going to be responsible for. For this one, I have H equal to 5e to the minus 200z times, why don't you just tell me what this is, so, times cosine, right? And what, cosine of, what is it, 2 pi times 10 to the 8th?
10 to the 9th.
10 to the 9th, sorry. T plus, or sorry, minus, and this is 200z, correct? And this is milliamps per meter. And is this AY or AX?
AY.
AY. All right, now if we have that, let's talk about going right to the phasor domain. Remember, for the phasor domain in general, and I want to try to make sure I can relate this to the circuits model. If you had V right here in circuits equal to like a magnitude V naught, just cosine of omega t right here plus some phase angle. What you would do if you wanted the phasor form of this, you would take the magnitude, put it down here, it would be the angle phi. Y'all with me? Now, what this really is, it represents the real part. Here, when we go to the phasor domain, do you remember this problem, by the way? This problem? Some of you. All right. Here is the magnitude. So H phasor would be 5e to the minus 200z. And remember, it's the scalar value. That's e to the minus 200 is a real number. You all with me on that? Admittedly, it's decaying in magnitude, but it's a real number. Now, there is no phase angle, right? Correct, class? But, I mean, there is no phase angle like this. Here's the phase angle. Right? That's the theta, or phi. Are you clear on this, everyone? All right. So this would be what? E to the minus j, and this would be 200z. And then it would be milliamps per meter AY. Now that would be the phasor form of that. If you didn't put this in, I didn't take much off, maybe a half point of a point. But you had to at least understand how to get to the phasor domain. Are you with me, class? Now, once I have that, and there's a variety of ways to go where I'm going. The next thing I want is to get E. Well, I see the direction of propagation by inspection is going to be the z-axis, isn't it? It's going in the positive z direction. You with me on this, class? This is just basic propagation. Everybody with me on that? How I get it? I look at the coefficient of the spatial argument. And if it's a negative beta, it's going in a positive z. If it was a plus beta minus z. Correct, class? All right, so now I say this is just AZ. And now to get E in the phasor domain, and you can do it any way you want, it's minus eta, right, the intrinsic impedance of the region, times unit vector in the direction of propagation crossed H. That's one way to get it. We can also get it by saying I know it's going in the z direction, right? Therefore, E crossed H would be the direction of propagation. I could get the direction of propagation that way. Do you agree with that? I mean, excuse me, the orientation of the E field. We've got this. How do we get eta? Well, what do we know about this one? This is important. When we look at this, beta and alpha are the same. So, if alpha equals beta, right, and this is chapter 6, you know it's a very good conductor, don't you, class? Right? If alpha equals beta, it's a good conductor. And that means, what? Well, in general, if you have gamma equal alpha plus j beta, that's equal to square root of j omega mu over sigma plus j omega epsilon. But since alpha equals beta, you know the j omega goes away, don't you? Right? It's a good conductor. And therefore, I can say that alpha equal beta would be equal to square root of pi f mu sigma. Now, we can get it by doing this. We can go ahead and multiply this out. And but frankly, remember, this is really what? This is equal to 1 plus j divided by the square root of 2, right? Times this, which is equal to the square root of omega mu sigma. Now, if you look at this, you could take the square root of 2 in here, you get 2, and omega is 2 pi f. Correct, class? So that's where I get this. So alpha equals beta. To get f, if you look at the argument of cosine, you see omega is equal to 2 pi times 10 to the 9th, and therefore f would be equal to omega over 2 pi, or it's equal to 10 to the 9th. Do we agree with that? I'm just going through the method. Right? Everybody with me on that? Now once you have that, then the next thing you have, since I have f, and I have alpha and beta, right? I can get sigma, can't I? Because I said it's non-magnetic. So then I can say, if I take alpha squared, whatever it is, and divide it by pi f mu naught, now I get sigma. And that value I've stated in there. I forgot exactly what it was, to be honest with you. So that's 10.132. Right, 1 over ohm meters. And now I can get eta. And eta is square root of j omega mu over sigma plus j omega epsilon. But because it's a good conductor, we can get rid of that. Correct, class? And most of you got this part right, I think. So that means I have square root of j, where I have just e to the j pi over 4 times square root of omega, call it 2 pi f, times mu naught over sigma. Now that's actually going to be 1 plus j over square root of 2 times this eta naught here, call this eta naught, right? Or you can put since eta naught e to the j. Some of you did this 45 degrees. Either one's acceptable, right? And eta naught would just be the magnitude of that. Do you all agree with this class? I think it's 27.915 ohms, right? Y'all remember? You see it on your papers, class? Now these solutions are up on the board, or I mean up on OneNote, and I emailed them to everybody. You agree with this so far? So that's that part. Now how do you get phase velocity? Oh, by the way, when I get that, I can do this, and what is it going to turn out to be? It's equal to minus that eta naught, which is, I'll just put it like this. Minus magnitude of eta naught times AZ crossed into H, and that's crossed into the 5 e to the minus 200z e to the minus j 200z, and that's AY milliamps per meter, and that goes away, it becomes volts per meter. It's millivolts per meter then. This is only one way. There's several ways to get these answers. And therefore, E in this one, when you go through it, I got AZ crossed AY is minus AX to the minus I is plus AX. Magnitude of eta naught times 5 times 10 to the minus third here. And then it's going to be e to the minus 200z, e to the minus j 200z. But this phase angle here, it's really eta naught, and the phase angle is 45 degrees, so it would be times either e to the j pi over 4 radians or e to the j 45 degrees, either one. You have to include the phase angle. You with me on this? A lot of people had problems getting eta in this one. I think a lot of people got the frequency right because they just looked at the coefficient of t, but they had a problem getting eta. Are you all with me on this class? And it comes from the fundamental understanding of how these equations actually work. And good conductor, as soon as you know that, it's sort of over. Any questions about this before I continue? Has anybody looked at the solutions on OneNote or on your email? You can see them? Mm-hmm. Okay, they're there. And I use MathCAD, so the rendering of everything is, the formulas show the symbols except for eta, I think I placed ETA or something. Or eta not, just N0. All right, problem 2. You good with this? Yeah?
How are you supposed to find the phase velocity?
Oh, I'm sorry, I didn't put that down. Well, phase velocity is always what? Omega over beta, right? That's the standard phase velocity. We could derive it, but we don't need to. So it doesn't matter if it's good conductor, lossy dielectric, or perfect dielectric. So omega here was 2 pi times 10 to the 9th. Thank you very much. Divided by beta, which is 200, right? And that's pi times 10 to the 7th, isn't it? Mm-hmm. And that would be meters per second. I mean, that's the way you always get it. If you're wondering about how to get it, this is the phase, 2 pi times 10 to the 9 t minus 200z. Set that equal to phi and just take a derivative of that with respect to t. You're going to get dz dt, which would be the phase velocity, right? And that would be equal to just 2 pi times 10 to the 9th. And then you divide by 200 and get that. Divide by beta. All right? Now, problem 2. Is there anything going on today? Problem 2 is the shield. And this is a thick shield. So here we've got a shield of thickness D, and we have an incoming electric field. And then we have something here that has parameters sigma, epsilon, mu. This is air, and this is air. We're going to go through the whole 9 yards of this one. Make sure you know this, because you're going to see this again. We can put in the values at the end. The frequency and all that stuff won't matter. It's a very good shield. Can you all see that this is sigma is equal to 10 to the 6, either 1 over ohm meters or Siemens per meter, right? That's extremely good conductivity. Do you agree with this? Then you can figure out the skin depth is 1 over square root of pi f mu sigma, or 1 over alpha. And this is going to be, I don't know what it is, but it's much, much less than the thickness B, which is 10 to the minus 4th, I believe, meters. Correct, class? So it's a thick shield. You all agree with me? Now, when we do this, the first thing I asked about, give a frequency equal to 10 to the 8th hertz, or 100 megahertz, right? So here's the thing. When I look at this, the first thing I asked for was the power density of the incoming wave. That's in air, right? So that's going to be 1/2 magnitude of the incident E field squared over 8 to 9. The majority of people got this right. Do you all agree with that? We could find the H field, and we could go 1/2 the real part of E cross H conjugate, but there's no need. Agree? So when you do this, the incident E field was 1 volt per meter, right? So this is just 1 over 2 times 120 pi, and this would be watts per meter squared. Does everybody agree with that? You don't even have to put a direction on this one because I asked for magnitude. All right, that's the incoming. Now, the next part, I have to get eta shield here, right? I need that. Oh. So what is eta shield? Well, eta shield is equal to square root of j omega mu over sigma plus j omega epsilon. Do you agree with me? Everybody? Now there's one caveat here. This is a very good conductor. You could go ahead and put in epsilon omega, but it's going to make no difference. Do you follow me on what I'm saying? Everybody? So when you do this, you don't have to have this because it's so small. You could include it and will not change anything. You can try. You don't believe it. So if you did that, it's fine. You don't need to. So really this is what? This is going to be e to the j pi over 4 radians, or 45 degrees. And then it's going to be square root of omega mu over sigma. You can write that as square root of omega mu over sigma, and just put it at 45 degrees. It doesn't matter. Are you with me? Now remember, that's a complex number. That has a real imaginary part, correct? This is real important. Is everybody with me so far? Calculating eta shield, right? Now once we have eta shield, the next thing we need to get is the transmission coefficient at boundary 1, and I'll label this boundary 1. and the transmission coefficient in boundary 2. Correct, class? I want to make sure, because people mess this up. And I think it's because of the complex number. I'm not certain, but I think it was that. So, when I look at this, admittedly, you could say 1 plus the reflection coefficient of region 1, but in general, it's easier to just, in my opinion, to do this. 2 times the impedance you're going into, right, over the impedance you came from. Agreed? With me? You could have 1 plus the reflection coefficient, but the reflection coefficient is going to be almost 1, and if you don't have your calculator dialed up where you have the tolerance level sufficiently high, you might get an error. Now when you do this, this is eta shield. What does this come out to right here? I actually forgot.
Oh, yeah. 0.2 plus J. 0.2. Or 0. With 0. Yeah. 0.0.
It's really 0.028 at 45 degrees. So this is 0.028 at an angle of 45 degrees ohms. Now, we're rational beings. If you look at this, 0.028 plus 8 knots, 120 pi about 377 is about 8 knots. Do you agree, class? So no matter what approximation you make, you get the right answer. So this is really about 2 times eta shield. So it's 2 times 0.028 at an angle of 45 degrees. Remember, this is complex. Over 8 knot, or 120 pi. That's about what it is, and it's going to be almost exactly that for this problem. And that means the reflection coefficient, or the transmission coefficient for this one, is about 1.491 times 10 to the minus 4th. At an angle of 45 degrees. This will enter in a second, but it's not right here. Do you all agree with me? Let's go ahead and get the reflection or transmission coefficient here. This is tau 1 that I got. Now tau 2 is 1. That's transmission coefficient boundary 2, correct? What is that always? The impedance you're going into times 2, right? So that's going to be equal to 2, what's the impedance out here there? 8 naught, right? 2 8 naught over 8 naught plus eta shield. Does everybody see that this is about 2? Because eta shield is so small. You add 8 naught to it, it's about 8 knots. So the 8 knots cancel. And this is about 2, correct? I want to make sure you see this point. Right? Now, be with me on this part. So now, when I take a look at the transmitted field right in here, this is what I wanted. I wanted to know what E was right there, just inside of the shield, and I can call that E prime, if you will. Well, E prime here, the magnitude at least, would be what? This is just inside the shield, would be the transmission coefficient, right, times E naught incident. Do you agree with me? Right? Now that's a very good conductor too, right? And I know if that's the E field, just I want you to pay attention to this next part to make sure. I didn't take anything off if you got this part right here. I mean, what I'm about to show you, if you didn't include this. But if that's the E field, it's about what? 10 to the, or 1.49 times 10 to the minus 4th volts per meter, just inside, right? Now, please pay attention to this part. But what's the H field? Well, the H field is actually going to be, and you can put the E to the, well, no, I'll tell you what, just leave it like that, Maggie. Well, the H field is going to be it's really going to be the E field, right? Or it's actually going to be the direction of propagation divided by eta crossed into the E field right there. It doesn't matter what's going to happen to the E field right here. Whatever direction the E field is, the H field is orthogonal, so the directions don't matter. But this does. And that means the H field right here will be equal to E prime over the magnitude of eta, right there, whatever it is. And that would be eta shield. But now the phase angle will be whatever the angle is on the E field prime, and it will be e to the minus 45 degrees. Now also when we did this, when we talked about E and H in a conductor, there's going to be a 45-degree shift. And here's what I really want you to take from this. So in part 3, let me erase this. Please write this down. Only a few people got this part. I didn't take off for it on this one, but I will on the final in the next couple exams, or the next. So when we talk about what is the incident, the power density prime just inside the shield, just inside the shield. Well, that's going to be 1/2, right? And then technically it's the real part. I'll just write this down for completeness. But really, if you look in your book, some people had this right. It's 1/2 the magnitude of eta shield, right? And then it's going to be times the E field, prime magnitude squared, times the cosine of 45 degrees. Because that's the angle of eta. Do you remember this class? Remember that cosine of the angle? Now, admittedly, you could put down times e to the minus 2 alpha z and put it in the direction of propagation. You can call it AZ. You don't need this because I just wanted it just inside, so it didn't propagate it. I just wanted it on the other side, right? Now, if you didn't have this, I didn't take off because this angle is associated with the angle associated with the shield impedance, correct? And so I want to make a mention of this. If the shield impedance had an angle of 0, in other words, if it was lossless, then the cosine of 0 would be 1. It would just be 1/2 magnitude of E squared over eta magnitude, okay? I gave people credit for that if they put that down. They got the right value of E. But you have to get the E field just on the inside. And the thing people forgot is that this transmission coefficient right there has an angle of 45 degrees here. So when you take the shield impedance, you know, when we get this transmission coefficient right here, well, frankly, when you do this, you had to make sure that you included this. That's, I guess, what I should say. If you did, some people did this. They said that the reflection coefficient was eta shield minus eta naught over eta shield plus eta naught. Now, they took as eta shield strict real. They didn't go ahead and put in the actual complex number. So when they got this is equal to 1 plus the reflection coefficient, they got an error. I mean, it's wrong. I got you on that class, so you have to include, when you're dealing with shields, low impedance values for good conductors, you have to include the angle to do these calculations, okay? I don't know how many made that mistake here, but there are a few, and I want to make sure you're clear on that. After that, what was asked for? Oh, the magnitude of the transmitted E field. Okay, I'm going to do it over here. I'm just worried about magnitude. Okay. So first I want to take the E field inside here, okay? Right? And that's just the transmission coefficient at 1. Now you know what happens. Once it gets in here, the magnitude of this E field starts decaying as e to the minus alpha d. Agreed, class? Right? And alpha, of course, I can put this down. Alpha for a good conductor is beta is equal to square root of pi f mu sigma. If you don't remember that one, always remember gamma is equal to alpha plus j beta. And gamma, and this will always work, square root of j omega mu sigma plus j omega epsilon. No matter what, good conductor, bad conductor, perfect dielectric, whatever, you do this, you always get alpha and beta. And if alpha and beta are equal, it's a good conductor. Okay? Everybody? Now, getting back to this thing. So, if I want the transmitted E field, I take the transmission coefficient of reaching 1 times the incident E field magnitude. Do you all agree with that? Then, as it's going through, it's decaying, so you have to put e to the minus alpha. Well, z in that case would be just d, isn't it? That's how thick it is? Are you with me on this? That's the attenuation the electric field would have. And then you have to take this times the transmission coefficient in region 2, correct, class? With me, everyone? Now, once I have that, just take the whole magnitude, right? So that's the transmitted field. We've got the magnitude of that wherever it is. I put that down. It was like 1.49 times 10 to the minus 4th, correct? So this is going to be about the magnitude of E transmitted is about magnitude of 1.49 times 10 to the minus 4th times magnitude of 1 times exp to the minus, in this case would be alpha, forgot exactly what that is, times the thickness d. And then it's times 2. And that's it. When you go down and do the math on this, I don't know how many people got this right. You get an electric field magnitude of 40.88 microvolts per meter, if you do the math, correct? So this is 40 microvolts per meter. Agreed? Now that's the field just on the other side of the shield. That's how much is coming out. Now look at the magnitude reduction. That's almost, what is that? That's better than 5 orders of magnitude, 5.5 orders of magnitude, correct, class? It's down by 10 to the minus 5th. That's a huge amount of reduction, correct? That's the electric field. Y'all follow me what I'm doing here, everybody? If you have questions, now ask. Now once that's the electric field, that electric field is out in free space, right? So if you got that right, what is the power going to be? The actual, that's the electric field. I guess that was 4, I'm not sure. Now if we want the power transmitted, we're in free space, so now we're free to use 1 over 2 magnitude of eta naught, just 120 pi, and then times E squared, so you take E transmitted here, and just square it. Do y'all agree with this? Because it is in free space, right? So just take 1/2 E squared over 2 eta naught, because now eta naught is the impedance. I'm going to say one other thing too. Please make sure if you're dealing with something that's propagating in a lossy region or you're unsure, use this equation for attenuation. I'll put it down here so we're clear about it. This was on problems I gave you early on in transmission through a good conductor. So in general, if you have a conducting region, I mean sigma unequal to 0, then the power density for a sinusoidally driven wave would be equal to 1/2 magnitude of the E field propagating through that region divided by magnitude of the intrinsic impedance in the region. I'm going to call it eta S. Now, if there is something where they want to calculate power intensity, like at the middle of the shield, then it will be e to the minus 2 alpha times z, where z would be the depth into the shield. Are you with me on this? And then it's going to be times the cosine of the angle associated with the shield impedance. Now, that E naught incident you have to get, if it's a shield, by taking the transmission coefficient times the actual, better call this just EI, or yeah, EI here, and times the magnitude of E naught incident right there. And that can be a very small number. Agreed? All right. Is everybody okay with this? Now, I know that people got it, there are people who got it completely right, but there were a lot of people that made a lot of mistakes with the intrinsic impedance calculation of the shield. Please make sure you go through this and know what mistakes you made. Now, for 3 is the waveguide. This one I gave a whole lot of credit for because there are actually 3 possible modes of propagating. Hold it. I want to say it. But we got the O1, the 2O, 1O, 2O, and O1 mode. There are no TM modes in this one. And I'm going to go through this and make sure you're clear on this. Now, this one, I gave a whole lot of benefit of the doubt because I should have said what modes, not what mode, and the impedance of the mode. So if you had any mode correct and you had the right impedance, phase velocity, and stuff, you got full credit. But if you put like TM11 or something like that, then you didn't get much credit because it can't be a TM mode, and I'll get to that in a second.
What was the curve again, one more time, if you don't mind?
If you take your raw score out of 45 points and add 4 points,
Okay.
that's correct. Or take your percentage score and add 10, because each point is 2.5 points out of 100.
Okay.
Make sense?
Yes.
And that makes the high grade 110, and I don't know how many people are over 100 to be honest. Sure. Try to get a good eraser next time I come down. All right, so this problem had a standard air-filled waveguide. I didn't even ask for impedance for the load on this one because I figured the calculation would be too long. And maybe on the final I will. And I have dimensions A, right? And height B. This is a classic rectangular waveguide. Well, the cutoff frequencies for the M and mode are really going to be C, well, better do it this way. It's going to be 1 over 2 square root of mu epsilon, all right, times the square root of m over a squared plus n over b squared. Right, everybody? Okay. We have A as 8.636 centimeters. And B equal 4.138 centimeters. Those are the cutoffs. Also, the driving frequency was 4 gigahertz. So when you go down here, the mu epsilon here, 1 over the square root of mu epsilon, you could write as simply C, right? Because it's air-filled class. Please make sure you understand this. With me? So I'm just going to write it as C. Most of you did this. Okay. Okay, now for the frequencies. This is just doing it on your calculator. FC10 was 1.737 gigahertz. FC20 is going to be 2 FC10, right? And that's equal to,
3.474 gigahertz.
thank you. And then FC01 would be equal to,
3.625 gigahertz.
thank you. And finally, FC11, which is the first TM mode, because TM have to have a 1 and a 1, both for M and N, or else the sine function goes to 0. So you want to tell me that one?
It's 4.02 gigahertz.
Right. Which means only this one, and this one propagate. That's it. Now, after that, I ask for the phase velocity, right? Not the group of energies. So I'm going to go ahead and get K, and it doesn't matter which K you use. I have all these listed on the on OneNote, and I emailed you these. But if you look for K, I like this because I can just calculate this and use it over and over again. That's the square root of 1 minus, it's going to be the actual cutoff frequency of Mn, so of the mode numbers, divided by F squared. And here, maybe I should put that as K Mn. Right? And K10, K20, K01 are
0.901, 0.496, 0.423.
okay. Those are the K values. Right. So now I ask for the velocity. So I'm going to leave the K's like this. This is the way I laid it out. Next thing, when I look at phase velocity, right? Phase velocity is going to be C divided by K, right? And for these,
The first one is
7.096 times 10 to the 8th meters per second.
3.33 times 10,
Oh, sorry.
10 to the 8th. And then 6.05 times 10 to the 8th. And then 7.09.
What's the next one?
Okay, 6.051 times 10 to the 8th. And then the last one, 7.096 times 10 to the 8th.
Yeah. And then the impedance, by the way, these are TE modes. And I gave you credit, no matter what mode you had. You did TE10, TE20, or TE01. Any of those modes you got credit. Now, the numbers below there have to represent that mode. I don't know if anybody did all the modes. Right? Any one of those is fine. So next, after that, I asked for the impedance. Well, the impedance of the Mn mode is really going to be A0 because it's air-filled, and it's divided by K, correct? And these are all TE modes, so it's divided by K. And you can look down there. I have them. So the 10 is 418.5.
20 is 760.425.
10. 2001. Go ahead, you can do it.
760.425 and 891.707.
Any of those you got credit. Assuming it's if you put the 2.0 mode, 01 mode, or 1.0 mode, and the corresponding K and Z values, you got credit for V and Z. And after that, beta, right, the last part was beta in the guide. And beta in the guide is...
For 1.0.
I mean, first it's what? Beta unguided times K, right? All right. So for the beta in the guide of the 1.0, you can go ahead and tell me.
75.465. 2.0 is...
And that's radians per meter, by the way.
2.0.
Beta guide 2.0, go ahead.
41.533.
Radians per meter. And finally, beta guide 01.
35.418.
Radians per meter. I'm glad I put this down to talk about it. Remember, if we were calculating the impedance of a finite length line with a load, these different values of beta would be critical, right? Because the length itself of the guide would be in meters, and you would have to have the right load. By the way, if I give you a problem with a truncated load, then I'll make sure only either 1.0 mode propagates, or I will specify the mode propagating, okay? I'm not going to let you have to do that. So that was problem 3. Y'all with me on this class? And I was just plugging shot going down, making sure you understood this. This is not... Yeah, I'm sorry. Finally, the last problem was probably, of them, it was the one that you felt... I saw the overall best success, which I mean, people did this problem very well, thankfully. And you did have this recently, so I didn't understand it. Let me go through this, try to finish it. So the last problem is literally a homework problem with one exception, halfway. I mean, actually it is a homework problem. I did put a halfway. So I put a halfway dipole right here. And then I put a distance of 4,000 meters. And then I've got a short dipole here. And this is the length of, for L equals lambda over 20. And after that, I give you a frequency of 1 gigahertz. It means lambda is C over F, and that's going to be 0.3 meters. And I'm going to go through this one fairly straightforward. Now I gave you the directivity or gain of both of the halfway, so you didn't have to do that from memory. I want to warn you about something. I think some people, even with the right formula, they were in the wrong mode when they put down the angle. Either they had it in radians or there was some foul up. So let me go through this and just tell you. First they say that the radiated power, total radiated power on this one was 200 watts, is that right?
Yes.
All right, so now we want just the intensity of power right here. Right there. So I can say the incident power density, or PAD, would be equal to the radiated power density divided by 4 pi r squared. R, of course, is 4,000. And then it's going to be times the directivity, which is 1.64. And then it's going to be the cosine of pi over 2. Now, this should be in radians this month. Cosine of pi over 2 times cosine of, put this angle down, 60, right? So it's times cosine of 60. This whole thing is going to be squared over the sine of 60. Right? So that's, I'll put the formulas down, the answers I give you. Y'all agree with that, class? Just the gain or directivity times the isotropic power density. That's the power on target. Now, I think I asked for the electric field.
Yes.
All right, well, the electric field, this is free space, so you know that 1/2 magnitude of E squared, whatever the E is associated with, over 8 is equal to P incident, and therefore the magnitude of E on that antenna, second antenna, would be equal to the square root of 2 8 times the incident power density. That would be in volts per meter. I didn't care about any kind of vector notation here, just wanted to see what the values were, right? Finally, when I have that, the last thing I wanted to do, and this is the one I gave you, the P actually received would be equal to lambda squared over 4 pi times the gain or directivity of that antenna. That antenna was a short dipole, right? So for a short dipole, it's going to be 1.5, right, times the sine squared of the angle, which is 80 degrees. Right? I want to make sure I put degrees down. Degree, class? So this is one of these things you had to know if it was degrees or radians. You had to adjust. The sine of that, and it's this times the, this is really the aperture right here, the effective area, times the power density, right, from the first part. So if you turn the crank on this, and a lot of people got this all the way right, I believe, you get 1.088 microwatts per meter squared for the first part. For the electric field, you end up getting 28.64, and that's going to be millivolts per meter. And finally, for the receive power, is 33 nanowatts total power received. The one point you should have taken from this is that for transmitting 200 watts, you get almost nothing out of that. You're down at 10 to the minus 8 watts out. Now that's because it's a low gain antenna, both in the transmitter and receiver. If you have high gain, you can get out probably 2 or 3% of the total transmitted power, maybe more. Okay, and we'll get to that later. I ran you over, I'm sorry. Any questions? If you need to go, go. About this, if you're going to ask me how I made this test up, I looked at the homework and the quizzes they did, and that's how I created this whole thing. All right, that's it. I didn't try to do something to give you something where you got to start with Maxwell's equations, drop stuff. If you made mistakes, please find out where you made mistakes. Also, I'm going to say this. If you, for whatever reason, blew it, you're not alone, all right? And you can still make a comeback and do okay. You probably still get an A, as a matter of fact. I've had people absolutely fail tests and end up with an A in the course once they get serious. But I'm just telling you this, all hope is not lost. But please realize, you have to do your homework between classes. The worst possible thing, I'm not saying, nobody here told me this, another person in this class told me, one of the problems that at least they perceive is that a lot of people don't work except for Thursday, if there's a quiz Friday, or before the quiz, and that will cause you to have huge amounts of gaps in understanding. You will forget things. It's working 3 or 4 or 5 times a week with formulas and doing stuff that you will retain. And I know this from experience. When I was a reviewer, I learned a hard lesson. I made sure every time I got homework I did it, and I did a lot more than just the homework problems. And you retain it. To this day, I probably can go through most physics and stuff like this. I was about 40 years and do it because of that.